Welcome back, everyone. This is the session 11 from the chapter of work, power, and energy. The topic is elastic collision in two dimensions. And this session is in continuation of the session number 10. In the session number 10, we have studied about the elastic collision in one dimension. Now, in this type of collision, that is elastic collision in two dimension, the objects move along different directions after colliding with each other. And I have drawn here one simple diagram in order to explain this type of collision. So here you can see that this is the object A and this is the object B, and after the collision these two objects are moving in different directions. So the initial velocity, or you can say the velocity of this object A before collision is u1, the mass of this body A is m1, and the velocity of this body B is u2, its mass is m2, and after the collision the velocity of this body A becomes v1 and it moves in this direction as indicated by this arrow, and the velocity of this body B is v2 after the collision and it moves in the direction as indicated by this arrow. So I have taken, this is the x-axis, here this is the x-axis, or you can say I have written it as x direction, and this is the y-axis. So since it is moving, now here I have indicated that this body A has is now moving at an angle theta with this x direction after the collision, and this body B is moving with a velocity v2 making an angle phi with the x-axis. So now these are the four important points which needs to be remembered in this topic. First thing is that in the elastic collision, the total linear momentum is conserved. We have already discussed it in the previous session also. It means that the total momentum before the collision is equal to the total momentum after the collision. Second thing, the total kinetic energy before and after the collision remains the same. The total energy is also conserved. And the fourth point is, that is, the forces which are involved in the collision of these objects are conservative in nature. So these are the four important points which needs to be remembered in this topic. Now considering these 4 points, now I will be deriving certain equations based on the first point, that is the linear momentum is conserved, that is the linear momentum before the collision and after the collision is the same. So what I have done is I have this is the velocity v1 of this object A, and it is making an angle theta with the x direction. So I have resolved this vector, that is the velocity vector, along the x-axis and the y-axis. So along the x-axis, its component is equal to v1 cos theta, and along this y-axis, it becomes v1 sin theta. The direction of this this velocity component is indicated by this arrow, that is, it is pointing upward. Similarly, this v2 is the velocity of the body B after the collision. So I have resolved this velocity vector into two components, one along the x direction and one along the y-axis or the y direction. So along the x direction, its component is equal to v2 cos phi, and along the y direction, its component is equal to v2 sin phi. Now this component is pointing downward, okay, as indicated by this arrow. This is the point of origin. I have taken, this is the point of origin, this is the x-axis and this is the y-axis. So now, since the linear momentum is conserved, so we will have to consider the linear momentum first along the x-axis, and we have to consider the linear momentum along the y direction also. So along the x-axis, initial momentum, that is the total initial momentum, is equal to the total final momentum, that is the momentum, the final momentum after the this collision. So the initial momentum is equal to m1 u1 plus m2 u2, where u1 and u2 are the velocity of this body A and body B respectively. Now, along the x-axis, the velocity component of this body A is v1 cos theta. So the momentum will be equal to m1 v1 cos theta, first thing, plus the velocity component of the body B is along the x-axis is equal to v2 cos phi. So the momentum will be equal to m2 v2 cos phi. So this is the first equation which we have got. Now we have to consider the momentum along the y-axis also here. That is along the y-axis. So along the y-axis, the initial momentum, that is the total initial momentum along the y-axis before the collision, is equal to 0, because these two bodies are moving along the x direction and before the collision. So before the collision, the total momentum of these two bodies along the y-axis will be equal to 0. Now, the total momentum before the collision along the y-axis should be equal to the total momentum along this y-axis after the collision. So this is equal to v1 sin theta. Now here you can see that these two velocity vectors, they are acting in the opposite direction. Therefore, since if I am taking this velocity vector as positive, if this velocity vector is taken positive, then this velocity vector will be taken as negative because it is pointing in the opposite direction. So minus, so this will be equal to that is v1 sin theta, this is the velocity, into m1 minus v2 sin phi into m2. So this is the second equation which I have got. And now, since the total kinetic energy before the collision is equal to the total kinetic energy after the collision, therefore we will be getting another equation, that is half m1 u1 square plus half m2 u2 square. This is equal to half m v1 square plus half half m1, here this will be m1 and this will go to m2 v2 square. So this is the third equation which I have got. Okay, so now what I will be doing is here, that is I will be writing these three equations here now. The first equation which I have got is that m1 u1 plus m2 u2 is equal to m1 v1 cos theta plus m2 v2 cos phi. This is the first equation which I have got. The second equation which I have got is v1, that is m1 v1 sin theta will be equal to m2 v2 Sin phi. So this is the second equation which I have got. And the third equation which I have got is here is, that is half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. So this half will be taken common on both the sides, and then it will get cancelled out. So the third equation, finally the third equation will be equal to m1 u1 square plus m2 u2 square, this is equal to m1 v1 square plus m2 v2 square. So this is the third equation. So these are the three important equations which we have been able to derive by using the two concepts, that is the total linear momentum before the collision is equal to the total linear momentum after the collision. Now since these two bodies are moving in different directions, so therefore we have equalized the total linear momentum along the x-axis and the y-axis. So we have got these two equations using this concept, and the second concept was that the total kinetic energy before the collision is equal to the total kinetic energy after the collision. So based on this concept, I was able to get this equation, or this equation can be rewritten as this, that is m1 u1 square plus m2 u2 square, which is equal to m1 v1 square plus m2 v2 square. So by using these three relations, if this theta and phi are known to us, if this theta and phi are known to us, we can calculate the other parameters, like see, there are the mass of the body is known, is normally known to us. The initial velocity of these two bodies is also known to us. So if these things are known to us, and if this cos theta and cos phi is also known to us, then definitely we will be able to calculate the velocity of those objects after the collision. So thank you very much for joining this session, and in the next session I will be coming up with a couple of questions based on the elastic collision. So till then, have a nice day. Bye.